So good morning everyone. I'm so glad that you all made it to a 10 o'clock Monday morning lecture. That is wonderful. Who did the homework that I said? Nobody's not brave enough to admit they didn't do it. Alright. So if I asked here who was confident, they'd be 100% certain what I mean when I say a path of stationary action. Who'd say that? 100% confident? They know what I'm talking about. Craig. Excellent. So I have a problem that there's terminology that I understand very well, saying things like parts of stationary action and that sort of thing, and I forget that you guys don't know that. So if I say a word that you guys, or say terminology like that, and you guys have no idea what it means, please tell me and I'll say it again or explain it, because if I accidentally assume that you guys know something and all of a sudden everybody in the lecture has no idea what I'm talking about, that's a total disaster. So the other thing that I wanted to say before we got started is that so for today, what's the best way to put this? So we're not covering too much content today. If I wanted to tell you everything that we wanted to say in today's lecture, I could probably do it in 10 minutes and we could all go early. The only thing is you guys probably wouldn't learn anything from doing it. In fact, there's a lot of science that's gone to show that doing this whole lecture thing, where I talk to you and you just listen to me, doesn't actually work at all. You actually learn absolutely pretty much nothing from doing this. So for today's lecture, I've passed around some piece of paper. I'd like everybody to have a piece of paper. I'm actually going to ask you to do some questions. The other key thing is that you need to be able to talk to the people near you. So can I get everybody to stand up for me? Alright, if you are sitting by yourself, there's nobody next to you, can you please move so you're sitting next to somebody, then introduce yourself to them so that way you're not talking to a stranger later on. If you're already sitting next to people, just introduce yourself to them and sit down. So many of you made friends, that's great. Now I can't get you to be quiet. So the other thing is that I really would encourage you guys to ask questions. If there's something that you don't understand, I can pretty much guarantee that if you ask the people next to you, they probably don't understand it either, which means that everybody doesn't understand. So if you have a question that you'd like to ask, feel free to just put your hand up. Now sometimes I get a little bit absorbed in what I'm doing, so if I don't notice you, feel free to give a bit of a cough, like to try and make me notice. If that doesn't work, just yell it out, and I'll turn around and hopefully listen to you and your question. If you want to though, feel free to ask the person next to you first, because if they know, then that's sorted as well. But I do highly encourage questions, and if I seem to be ignoring you, just make sure that I've noticed you. So, we've already spoken about the homework, and I'd say that probably the most difficult concept, the thing that I'd expect the most difficult for you guys to understand, is what do I mean by a stationary path? So that's kind of what I'd like to look at the beginning of today, so that way you guys can get a feeling for what that means. But before I do, I'll just do a quick recap of last lecture. So, last lecture, you might remember, we spoke about a few things. The first one was we spoke about the technical definition of what is a path. So just a reminder, a path has a starting event, which means it has a position and a time coordinate, and an ending event. And then everywhere between, at every time in between those two events, there is a well-defined position. So that's the technical definition of a path. Then we said in quantum mechanics, a particle takes all possible paths between measurements. So if I measured it, let's say a photon here and another photon over here, and I asked which path did it take in between, that's a fundamentally wrong question to ask. In quantum mechanics, it doesn't take a path. It takes all the possible paths. It actually does everything in between the two measurements. So we don't sit and guess, oh, what do we think it did? It's not like that. It actually takes all possible paths between the two measurements. So the way that we can calculate probabilities in quantum mechanics is that we assume, okay, it took all these possible paths, and for each path we assign a phasor, which is like an arrow that points in a direction. So all phasors for every path have the same magnitude. They're all the same length. The only difference is they point in different directions depending on the action associated with that path. We're going to look at that today in terms of light, because the reason why that's really good is for light, action is directly proportional to time. So we can say that it's just going around according to the amount of time that the light spent travelling from A to B. So we don't have to worry about this complicated action, we can just talk about the amount of time. So you guys can get the idea. Then we're going to move on to action in next lecture. Next lecture. Alright. So the way that we finally get the probability is we take all these different phasors, add them all together, head to tail, just like vectors, get the total length, you square that length, and the number that you get gives you the probability of that transition occurring. So then I also asked you guys to have a look at the videos. So just out of interest, who preferred, so there was two videos, who thought the first video was better than the second video? Who preferred the first video? Who preferred the second video? I preferred the second video too. I think the first one could be a bit confusing, but there's a couple of reasons why I wanted you guys to watch it. So the first one is it actually talks more about action in the first video rather than just time, which it talks about in the second video. So I understand why it would be a bit more confusing, because you guys haven't really had a chance to look at exactly what action is yet. But the key points from the first video, so it was Fermat's principle, that light rays seem to take the path of least time between 2 points. Technically that's actually not true, it's actually stationary time. I'll talk to you guys about exactly what stationary means in just a bit. So then we've also got the principle of stationary action. So this is a bit more general, this is for massive particles. And so just like light particles will follow, or light rays follow the path of stationary time, massive particles will follow paths of stationary action. And it showed you how you can go about calculating this numerically, finding these stationary paths numerically. The reason that this is important is you guys are actually going to be doing that in this week's lab. We're actually going to make you guys numerically do this. So it's a little bit of an introduction for what you're going to be doing. In the second video, it was just a few examples of how you can actually use this explore all paths concept and phasors to actually calculate some probabilities. So, and it showed you some everyday phenomena, including light reflecting off glass and the colours that you can see on a thin layer of oil. So, the first thing I wanted to get around is this whole idea of stationary. What do we mean by stationary? Has everybody heard of stationary in maths before, in high school maths? You might have heard of stationary points. Who's heard of that? Quite a few people. So I've got some examples here on the slide. So what we have is a stationary point is where the derivative is 0. So if you take a derivative, set that equal to 0, you've got a stationary point. So some classic examples are, we have a maximum, so at the top of the function, minimum, or you can have an inflection point. Now when you go to 3D, there's actually a couple of other types of stationary points you can have as well. Can anybody, I'll get you guys, talk to your neighbour for a sec, what other types of stationary points are there? So talk to each other, what can you think of? I've given you guys some time to think, some time to talk about it. Can anybody put their hand up and suggest to me a different type of stationary point, different to the ones we've got here? Yep, up there.
Saddle point?
Okay, a saddle point. Have you guys all heard of saddle points before? No. It's really hard to draw in 3D. So this one you can only get in 3D. It's imagine, so I have a 2-dimensional or a 3-dimensional. So in the plane of the board, it could be a maximum like that. But then if I was coming out of the board, it would be a minimum. So you can imagine it coming out like that. right there, I also have a stationary point. But it's not a maximum or a minimum. It's actually a saddle point. It's what we call a saddle point. And the reason is because it looks like a saddle, like a horse riding a saddle. So that's one other type. Does anybody have any other types of stationary points that they can think of? Somebody yelled out. Yep.
A bowl.
A bowl. So that would be like a minimum. Yep. So that would be like a 3D version of a minimum point. Yeah. So that's another type. Yes.
Flat plane.
Yeah, that's actually a really important one as well. If I have a flat plane like that, every point on that is stationary. It's derivative 0 everywhere. Those are the main ones I was thinking of. Does somebody else have more? Is it more? Yeah.
Maybe the contour lines.
Sorry.
Variation, the contour lines.
Okay. On.
Yes, on a hill or something.
So if you have a map and you have the contour lines.
Yeah. So the variation with respect to the height is
Yep.
0 on one contour lines.
Yeah. Yeah. Okay. That's actually a really good example too. So for those of you who've seen maps before, sometimes on maps they'll indicate elevation with. So if this is a hill, they say, all right, this is 100 meters above sea level, 200 meters, 300 meters above sea level. So even this would be stationary in this direction, going around like that, kind of in one dimension, but you could actually have a slope going in that direction there. So it actually wouldn't necessarily be a stationary point, even though there's no derivative in this direction, there is in that direction. So contour lines aren't necessarily stationary points. The point right at the top would have 0 derivative. So those are the different types of stationary points. So now we have stationary point. Oh, question?
Do you have something where it's an inflection in one direction and then the maximum one goes in the other direction?
I believe that that is possible, but I've never seen it. So theoretically, that sounds great, but I have never seen it. But that doesn't mean that it can't happen. So the next thing I want to show you guys is a mathematical trick. Sorry, was that a question? Okay. A mathematical trick. Have you guys all heard of Taylor expansions before? Taylor expansions? Okay. This is going to be, for those of you who haven't, I'm going to show it to you now, but I'm not going to show it to you in detail. This is going to be your bread and butter move in physics, and I'll show you why. So, do we have any mathematicians in the room? If you're mathematicians, you might want to cover your ears for this. So it so happens for any function, fx, you can write a Taylor expansion like this, where you can write it out as, if I have some sort of fx, I can write that as some sort of constant plus some sort of number plus x, c2 plus x squared plus c3 x cubed. And I can do that, and I'm just going to say I can do that for any function. Now the mathematicians among you may know that I'm lying and that I can't necessarily, it has to converge, but we're going to pretend that this is true. So I can have any potential I want, and I can approximate it like this, around a particular point. So, there's two kind of, the classic approximation that we like to use in physics is we like to consider limits, so cases where x is really big or x is really small. So in this case, if x is really, really small, like let's say that x is like 0.001, x squared would then be 0.00001. So this is really small. And then this one would be 0.000000001. So essentially all these terms are insignificant. We just forget about the rest of the series and we just say next to that point, we can just say that fx just equals this and simplify our mathematics dramatically. So that's why we use these Taylor expansions all the time. But if you have a stationary point, the derivative is 0. It means this term here actually goes away. And so our leading term becomes this x squared here. So the idea is if you're at the minimum of any kind of function, it doesn't really matter how nasty it looks, but something like that, all these minimum points here, if you're really close to the bottom of the well, it can be pretty well approximated by an x squared term. So you guys might have heard of harmonic oscillators. The reason why we study harmonic oscillators so much and the reason they come up everywhere is that in physics sometimes we just like to pretend that every minimum is a harmonic oscillator. And it's a pretty good first approximation. And, yes, question?
But isn't the x squared even less useful than the x?
Okay, but x, at the bottom, there is no x term.
What?
So its derivative is 0, so the x term goes away.
Oh,
That term actually disappears if you're at the minimum. So that means that this is actually the biggest term So I forget about the rest of it, and I just treat it according to the x squared term. And so this is how we kind of define stationary, is that if I make a small change, if I deviate a small distance away from this point here, the change in my height is going to go according to x squared, not according to x. So if you're not at a stationary point, the variation, if you move slightly to one side, the first order variation will be the dominant variation. Whereas if you're at the bottom, you only get the second order variation, which, like you said, is much smaller than a first order variation. So that's kind of getting at what exactly we mean by stationary. So now I want to try and apply this to some paths. So I want to consider materials of different refractive index. So these here are actually real photos. They're kind of cool. And as you can see, when light enters different mediums, you can get this kind of bending, which means you get things that look, what? Where's the head of the bear? Or in this case, the bottom half of the boy looks much larger than the top. So sometimes this is called the broken pencil observation, or the broken pencil trick, if you wanted to look up exactly how it works. But you can kind of get these discontinuities, because light will bend when it goes into a material of different refractive index. So we're going to consider the simple case where we have, let's just call this bit vacuum, and the top bit can be glass or air, it doesn't really matter, something with a higher refractive index. So I'm going to have a point B here, and a point A, and I'm going to consider a light particle going from A to B. So these are my endpoints, and I'm going to consider all possible paths between them. So what I want you to do is I want you to talk to the person next to you. What do you think is going to be the fastest, the path of least time between A and B? Talk to the person next to you. What's going to be the fastest path, the path of least time?
Yeah.
Somebody put their hand up and tell me what they think the fastest path is going to be. What the fastest path can look like. Yes?
From going A to B, it's going to be a little bit to the right of A to B.
Okay.
So it's going to go further to the right, and then it's going to hit the bar and head back up.
Yep. So the shortest path in terms of distance would be straight from A to B. But I'm guessing what you figured out is I actually travel faster in A than I do in B. So if I travel slightly further here, then I can avoid slowing down in this medium, in the higher refractive index medium here. So actually, I could probably go a little bit faster than that, even though it's longer, by doing something like this. Is that what most people thought? Okay, not everybody's got their hands up. Does anybody have any other suggestions for what they might think the fastest path is? Yes?
You could travel to a separate dimension at B and then reappear at A. Or the other way around, A and then reappear at B.
Oh god. Okay, does anybody have any other alternate suggestions? So yeah, I like the one that's drawn on the board, yes.
Well, it depends what N is. It could be faster and could be area.
Yep. So if it was
It could be to the left.
So if this was a lower refractive index than this, then yeah, it would actually be faster to take a short distance here and then go there and then a long bit. But in this case, we're just going to say that this is the higher refractive index down here with these, and then we have lower refractive index down here. So if we want to calculate the quantum mechanical probabilities, you guys remember that we consider all possible paths. So in this case, I'm not going to consider going into other dimensions and things. The reason is that luckily those paths will all cancel out. The phasors will just point in random directions once I consider all of them, and they'll cancel out. So instead, I'm only going to consider straight line paths that touch somewhere on this boundary. So I'll consider something like that. something like that. Parts that look like that. So, if you imagine, so obviously there'd be infinitely many, but let's just consider a small number, maybe about 10 or something like that, just so we can get a bit of a feel for what's going to happen. So, for each of these parts, I need to figure out what is the action of that path going to be, and sum the complex exponential. So I've drawn it as the stopwatch on there. Sorry if that's a little bit confusing, but just a reminder from last time, we have the function E is equal to IS on H bar for light, IT omega. It's much easier. So this is my stopwatch function, if you like. It just goes round and round and round according to time. So what I need to do is I need to calculate what's the time of flight going to be for each of these paths. So what I'd like you guys to do is, does everybody, I'll just remind you at the start, I handed out these pieces of paper for everybody. So if everybody, I want to actually see your answers at the end here. So can I get you to all get out your piece of paper, and what I want you to do is I want you to draw a graph for me, so something that looks like this. I'll just draw it in black so it'll be a bit easier to see. So on this axis I want to have time of flight. And on this axis, we're going to have where you arrived, so which of these different points you arrived. So I want everybody to take a minute or so, or we'll see how long it takes you guys to do it. And you can talk to the people next to you if it helps. I want you to create this plot for me. So this is where you arrived at the boundary. No, it's called position. If anybody didn't get a piece of paper, just chuck your hand up. Or if anybody doesn't have a pen, chuck your hand up, and I'll pass it around. So does anybody need paper or pen? Just chuck your hand up, I'll come around. Position, it just means where along here does the path go. So, like which of these straight line paths? That's what I meant by position for the x-axis.
Position 0
to be honest, you don't have to put numbers on it for me. So like, you can just, yeah, alright, you can call A0 if you like, I don't mind. Or you can say A somewhere, it doesn't really matter. So maybe I'll just give you guys, who haven't drawn it yet, like 10 more seconds to quickly draw what you think it looks like. question. Alright, I think that's enough time. Hold up your piece of paper, I want to see what you've drawn. Oh, that was good. Alright, so it looks like I'm going to go with the majority answers here. There seem to be a few different ones. The main two that I'm seeing are vols that look like that, so you've got some sort of minimum. So I assume that this minimum here would be our time of least, our path of least time. So maybe it would be that one there. The other one that I saw a few times was something that was a little bit like that, where it didn't really seem to go back up again. I don't think this second one is quite right, because if you keep going further and further along this way, then it's going to take even longer and longer to get to B, because you have to go further through both mediums. So I think that the vol is actually a pretty good approximation. That's what I had too. So something that looks like that. So I've decided that it could be glass or anything. So the key thing that I wanted to point out here is that this point down at the bottom is a stationary point. So mathematically, this is a stationary point where the derivative is 0. So translating that back to what does it mean to have a stationary path, the path that corresponds to that stationary point is the stationary path. What that means is if I slightly move my path to either side, like slightly moved it to either side, compared to the neighbouring paths, there would be no first order change. There would only be a second order change. So I just wanted to mention on that point, when somebody asked the question, for my Taylor expansion, they're asking why is this term 0 for a stationary path? The reason is that I'm actually showing you the simplified as a baby version of it. If you wanted to actually calculate these terms, what you do is you actually consider it around a particular point, like an x0. You can look this up on Wikipedia if you like. And the way you can figure out what this is you take the derivative of the function at x0. So by definition of C1 is equal to derivative of the function at x0. But because it's a stationary point, we're saying that the derivative is 0 at that point. So that means that this C1 goes to 0 and that term goes away for a stationary point. So that means if I moved to either side here, a small amount, compared to neighbouring paths, it would change as x squared, which is a smaller quantity than x, because we're considering a small deviation. The reason this is important brings me into the next thing I want you guys to do. Oh, sorry, question.
Why do we really consider paths that travel in a straight line?
So technically we should consider all paths. The reason that we're not is actually exactly what I want to talk about now, and I want you guys to do another activity that corresponds to it. So if your question isn't answered at the end of this activity, then ask it again. So what I want you guys to do now, we have this plot of position versus time. So I want you guys to chunk up your path into sections, like that. And for each of those, I want you to assign a phasor. Remember, for light, the phasor, the direction of the phasor, is directly proportional to the amount of time that is spent flying, or the amount of the time of flight. So, chunk up your path. Let's just say that the minimum points in that direction. I want you guys to draw what are all the other arrows going to look like for each of the other paths. All right, have a go. And you can talk to the people next to you as well, if that helps. Or you can do it by yourself. I've seen quite a few people make the same mistake now, so I'm just going to tell everybody, in case you've also made this mistake, you have a chance to fix it. Sometimes I get something where if I consider both of these, this one's pointing up like that, and then maybe this one here is pointing down like that. Oh, sorry. That one there is pointing down like that. However, these are at the same height. They have the same time of flight. So if my clock went around for the same amount of time for both of them, they have to be pointing in the same direction. So if these are the same height, then these should be pointing in the same direction is the idea. So now that you know that, I'll give you another minute.
Is your iPad graph?
Sorry, your graph is symmetrical. That's fine, but it doesn't have to be.
Oh yeah.
Yes, exactly right. Exactly right. You just keep thinking, why are you posting the same I think that's enough time. Can I get you to all hold up a piece of paper and I'll have a look, see what we got. Damn it, guys, I'm looking up to see. Oh, I'm really sorry, guys. I can see your parabolas, but I can't see your arrows. So, what I'll do is I'll maybe just show you the kind of correct answer. You can mark your own. So, for these parts here, so let's suppose this one's slightly longer. Oh wait, clockwise. So clockwise is that way. Yeah, so it'll start to point a little bit more this direction, then clockwise. Yes. Yeah, that's clockwise. So it takes a little bit longer to go this path.
The shortest time it faces that way. Shortest.
Because the shortest time takes 15 seconds or so. Then the longest time would have to take longer than 15 seconds, which would be the point.
Unless you're saying it goes through.
Agreed. So let's suppose the first one takes a whole minute and ends up pointing straight at the top. Then the next one takes a minute and 5 seconds and points slightly that way. What have I done? Oh, my original one's pointing sideways. Thank you guys. Alright. So in that case, it'll actually be pointing down a bit. Good work. I'm so glad you got that. Alright. Good work, guys. Alright. So this one might be pointing like that. Now the key thing is, the further you get away from the stationary point, the steeper this gets. So if it was only a small change for the one on either side, it's going to be a much larger change for the next one. So the next one might look something like that. Then once you get out here, it's getting even steeper again. So now, if I consider the next arrow, it could be pointing pretty much in any direction. So maybe something like that. Then the next one could be pointing something like that. The next one, maybe something like that. And essentially, like, if I consider paths next to each other, as I get to those steeper and steeper gradients, near paths that are nearby each other just start to go around the clock like crazy. The difference in time between these two paths is a lot less than the difference in time between those two paths. This gets steeper and steeper the further you go away, which makes sense, right? Because I have to go all the way here and cover that distance double when I come back. So, and I'll get some sort of similar thing happening. Once I get far enough over there, I start to just get, I'm going around in circles. So in the video, hopefully you guys saw something similar to this. It looked like that one there, where they actually did it with the stopwatch going around. And so, then what we need to do is we want to calculate the probability. We add all of the phasors head to tail. So if you do that, you get something that looks like this. But it so happens if I only consider the paths near the stationary path. So let's suppose that I only consider, you know, maybe those 5. So let's say there and there. I get nearly the same length. It so happens that I can pretty much just ignore all those other paths. They don't really make any significant contribution to the probability, because if I look at any section of those paths, it all the phase just makes it all cancel out randomly. So the only paths that contribute to the overall probability are the paths that are near the stationary path. Question?
Can you put like a numerical value to near? Like how do you take that?
Actually, and this came up last lecture, somebody else asked, what do you mean by constructive interference? I can, but it's kind of a grey area. Generally say if the phase is less than kind of pi or 2 pi, about that area, that's where we're still getting constructive interference. Once you're beyond that, then it tends to cancel out. You can tend to ignore that. So.
And is that just a random number, or is there any research or study going into that?
So the one that I just gave you there, I didn't read that off a paper, but it so happened, so that would correspond to pi is half a rotation, and essentially from looking like diagrams like these, you can see that after you get past half a rotation, you get like that. If you looked up papers, there's actually a book that Richard Feynman, he kind of was the person who thought of this explore all paths idea. He worked together with somebody called Hibbs and created, they wrote a book called Many Path Integrals in Quantum Mechanics, where he goes through and rigorously does all the maths behind this. I had to like read bits of it for my thesis, and it's really like high level maths, it's really difficult. And I don't want to confuse you guys with that, but if you are personally interested, there is at least one copy in our library that you can have a look at, and we can put the link up for that on Wobble if you like. Any other questions? Alright, so this is pretty much the key point that I really wanted to get across to you guys. This is the principle of stationary time, Fermat's principle. He actually thought it had to be a minimum. We're going to do an example in a minute where we show it doesn't have to be a minimum, it just has to be stationary. But this is what kind of brings us back to the classical world, the classical limit. But it so happens that if we're looking at a light ray, we only have to consider the stationary paths. The other paths don't matter. Question?
So why aren't we allowed to be light?
Sorry, why aren't we allowed You are. So you are allowed to consider wiggly lines, but it so happens if I considered, let's say, this wiggly line, and then I considered another wiggly line right next to it, the phase of those two lines is going to be completely random. And if I consider all of those, they're just going to cancel out. It's just like considering a path that goes all the way over here. Next to its neighbours, there's no overall contribution to the amplitude. Question?
Does that mean that you can consider like a maximum time?
You can. The only problem is that in these sorts of problems, you almost never have a path of maximum time. So I could go to the edge of the room and back, but then I could go even further and back. So it's very rarely that you get a maximum, but it is, what you're saying is correct. It's all about stationary, not about minimum. It's important. It just so happens most times it's a minimum. Right. So, going on from that, I did want to think about it in terms of classically what's going on with a light ray. So we were just talking about what happens in a quantum mechanical sense. And we just started to talk about, okay, so stationary parts are the only ones that contribute. That's what we see when we look at a light ray. So the question that I actually want to ask you guys is, when I see a light ray like that, what is it that I'm actually seeing? Alright, I'll take, somebody else has another go. Yep.
Oh, the light that bounces off the transport in the air.
Yeah, so when I see a light ray like that, and this is what we're talking about, classical light rays, I actually don't see the light itself. Like for example, you guys can see there's a projector up the back there that's shining light on the screen. If I look straight there, I don't see any light travelling up towards the board. However, if there's some dust that's just in front of the projector, like just above it, I can actually see the dust that's there. I don't know if you guys can see it. But if I see something like that, essentially what I'm seeing is I'm seeing bits of dust. Or in this case, the reason you can see it is there's some sort of dust or fog that's occurring. So when we see a light ray, what are we really seeing? We're seeing photons interact with these dust particles. So if I had one that was all the way over here and the light ray going from A to B, and it was blocking these paths, it's going to make very little difference to the probability of being found at B. Like, blocking these paths makes no difference. So the chance of the photon interacting with this dust is quite low. But if it's in the middle, blocking one of the stationary paths, that's going to affect my probability of B quite significantly. There's actually a good probability that will interact with the light, and that's why I see light rays, or why I see things like this, I see it along the stationary paths only. So it's just another way of thinking about Fermat's principle. So, what I want to do next is consider just one part. So, this is Fermat's principle. He actually thought it was minimum time, but it's stationary time. I'll take a question, so those of you who want to can write it down. Yes, question?
Is there a reason, because there is a probability that the light moves backwards, not on the stationary path.
That's correct.
So, do we actually see any photons from that then?
So, this comes back to the way, if we want to know what's the probability that the photon's going to interact with the dust, we actually calculate it exactly the same way. We consider all possible paths between the photon and the dust, but essentially, it's just like considering these crazy paths that go out there. If I consider all the paths to that, they all add up in random directions. All the phasors are pointing in different directions, and I get a very low overall probability of that happening.
So it can happen.
But yes, it could happen. Well, it depends if the probability is perfectly destructive. So if all the phasors cancel out exactly, then no. But if they don't, then there could be a tiny probability of it happening. All right, I'll take, wait a minute. Tell you what, we're going a little bit short on time. There's one example I really want to look at. If you guys have any more questions, you can ask me at the end, okay? So, this example I want to look at, let's just consider a single medium. So before we had this boundary where we're looking at different mediums. Now I just want one medium. So something like that. And what I want you guys to consider, so essentially the time of flight will still look something like that. If I've chunked up the paths like that, the paths that curve off will take longer. So it will still look like a parabola. Or it'll have a stationary point, a minimum time down the middle, and then the paths will get longer as I go further away. So now I want you guys to do this. So this is the last thing I'm going to get you guys to draw today. is I want you to consider what happens if I put in, so this is what the time of flight's going to look like. What will the time of flight look like if I throw in a lens or a piece of glass like that? The key thing about it is it's thicker in the middle and it's thinner around the end. So have a go, draw another one of these time of flight things. I'll rub out mine. Yes. Can you catch?
I'm pretty good, but how do you do it?
Terrible. Oh yeah. And so rather than position of the down. You got 10 seconds, finish drawing your picture. I want to see what it looks like. Use a nice big pen so I can see this. Alright, hold up a piece of paper. I want to see what you got. Oh, interesting. Interesting. Oh, that's the one. Alright. Okay, so some people got, I'm just going to tell you, the reason, this is actually how we design the shape of lenses, is the whole idea is that we figure out the thickness of the glass in such a way that that's a straight line. That every point there is stationary. If I did that, then that means that all the arrows would be pointing in the same direction, and it drastically increases my probability. So that's just like you guys have probably burnt ants with a magnifying glass. How you can get, increase the probability of those photons arriving on the ant. So this is exactly the idea. If I have it as a straight line like that, every point is stationary, I get perfect constructive interference. And they actually use this principle of stationary time to design, okay, how thick does my lens need to be at every single point? So I will finish there. This was my last lecture with you guys. So, thanks guys. So Craig will be taking over next lecture. If any of you did have questions, that's absolutely fine. I'll hang around just outside and you can talk to me at the end of the lecture. Please, I would like to see everybody's answers. So if you could just leave a piece of paper on the bench here on your way out, I'd really appreciate it. Thank you everyone, you've been great. I really appreciate your participation.